Hey there everyone, so we're going to look at the thyroid gland today, and we talked a little bit about how the thyroid is shaped like a butterfly, and hence why I gave you a butterfly picture. The middle of the butterfly here is basically what would we equate to the isthmus of the thyroid gland. And we've talked a little bit before about how the hypothalamus is not a pure endocrine gland. The thyroid is, however. So it has no other functions but to produce hormones, and that means it's going to need lots of blood supply, because one of those big rules for an endocrine gland is to release those hormones into the blood. Inside our thyroid gland, we see that we have something called follicles. These guys are going to hold on to iodine. So we need to be consuming iodine in our diets to acquire enough to keep our thyroids going. Otherwise, we're going to get a goiter, which may be good in some instances in some people, but it's really not good for your health. Our follicle cells, their job is to make something called thyroid globulin. So this is what is going to be our starting point for our thyroid hormones themselves. Then we have nearby the parafollicular cells, and they are going to make calcitonin. Now we know that calcitonin has nothing to do with our basal metabolic rate like our thyroid hormones does. Instead, it has to do with calcium. And so we're going to have a little look at how calcium and parathyroid hormone and calcitonin interact together to keep that steady within our blood. Here is a picture of basically the thyroid itself, and it shows you the location here in the neck. And we know that it's covered anteriorly by the thyroid cartilage to give it a little bit more protection. You can see it really does look like a butterfly. I haven't mentioned that the parathyroid would be located on the posterior side in here. You would have 4 to 6 little nodules on the posterior side of the thyroid where your parathyroid is. And then over here we can see that we have our colloid little follicles. So these guys are full of our iodine and the follicles containing the iodine. And then the follicular cells are here on the sides. And then we have the parafollicular cells on either sides of them. And so we can see that they're all nestled in there together. So the follicle cells are going to make your thyroid hormones. The parafollicular cells are going to make your calcitonin. So what we know about our thyroid hormones is that these are our major metabolic hormones. They are actually broken down into 2 kinds, thyroxine, which is our T4, if you've ever noticed that on your blood work. And this is mainly what we make in our thyroid gland. So our T4s are going to be mainly what we produce, but we also produce a few triiodothyronines, say that 10 times fast, and these are T3s. So when we look very briefly at how these guys are made, we'll see that there's a few T3s made by the thyroid itself, but most of our T3s are made at whatever organ it's arrived at, our target organ, by converting it from a T4. So you can just lob off one of those iodines and away you go. Now, our thyroid hormones work on almost every single solitary cell in our bodies. And when we're children and growing, they do actually work on every cell. And then as adults, although they have some mild effects on the adult cells, because we're already developed and grown up, they wouldn't necessarily have any detrimental effects. So our adult brain is already formed by the time we're adults, hopefully. And so if you have thyroid deficiencies, then they will manifest more as, maybe a mental lethargy than a cognitive delay, that sort of thing. Some of our functions, like I said, are mainly centered around our basal metabolic rate. They also help make us heat so we can survive our long, cold, miserable winters. They help to break down some glucose, and so we will want to use our glucose for metabolism, obviously, and we can break it down from our glycogen stores in our liver or in our muscle cells, or we can use our fats to break them down and release the glucose that's stored in there. And in worst case scenarios, we can break down our protein and release some energy from there. But it's hard work to make protein, so we want to look at that one last. We're going to regulate our tissue growth and development, and this is true of our skeleton, our muscles, and of course our nervous system too. And of course, it helps to promote our normal functioning of adult cells. That includes our brain and nervous system, our cardiovascular and muscular systems, and really all of our cells and tissues will be affected by the thyroid glands themselves. So this part I mentioned we would go over pretty briefly, our synthesis of thyroid hormones. So there are, 6 processes where you're going to start off with forming and storing some thyroglobulin, that precursor to the thyroid hormones themselves. Then you're going to need to trap some iodine in those follicular cells, and you'll actually actively transport it in. So you're going to really want to get some iodine in there and then oxidize it to form an I2. So we have never really talked about our chemical reactions, but we have something called redox reactions. So something gets reduced and something gets oxidized. If you would want to see a form of oxidation, of course, you can go see the copper roofs at Parliament, and they are oxidized, meaning somebody has stolen an electron basically from there. And so something else grabbed it or reduced that ion, and now we're going to oxidize the other one and steal it away. So in this reduction oxidation reaction, you take 2 molecules of iodine negative and form an I2 as they bind together. I wouldn't worry about that too much. It's just to briefly explain what oxidation is. And then iodination, so you basically come in and you add some iodine to the thyroglobulin to make these again. If you have 1 iodine, you have a monoiodotyrosine. If you have 2, you have a diiodotyrosine. So you have 2 iodines on here. So from there we can do some simple math and come up with either some MITs and a DIT to make a T3 or 2 DITs to make a T4. So it's a simple, combination of the different permutations and combinations of the single unit iodines versus the 2 unit iodines. Once that happens, you collect them all together, put them in a little package, and then you're going to form a nice little lysosome, which can easily then be exocytosed from there into basically our nice T4s, mainly what we're going to be producing out of our thyroid, or a few T3s. Any other T3s can, as we say, be made in the target cells, further out anywhere else in the body. So this little picture, of course, shows you exactly that. So, you have your iodine, it gets brought in. Our thyroglobulin has been made here, and together it goes through the packaging Golgi apparatus that together will take these little iodines, and voila, you have a whole bunch of them being made together to either form a DIT or a T2 or a T1. Then you can match those together to make 2 DITs. Sorry, I'm losing my voice here. To make your T3s or your T4s, package them all up in the lysosome, and then you can exocytose them or just send them out back into the bloodstream to then go to their target organs from there. Now, obviously, you are being told to do this from thyroid stimulating hormone. So our thyroid stimulating hormone, as you remember, this baby is coming up from the actual anterior pituitary, as told by the thyroid releasing hormone coming down from the hypothalamus itself. So the thyroid stimulating hormone is going to be then constantly telling the thyroid to be making more thyroid hormones. So you need to make sure that you have enough hormone there to tell it to do its job. You need to actually have enough T3 and T4 transported in the blood to actually go through and deliver it to the target organs. I'm just going to note that I did not put this wine glass here. It was the one that the design ideas came up with from PowerPoint, not me, although obviously I kept it. And then we have our T3 going to our target tissues. It binds a little bit better once it gets to the target tissues. That's why our T4 can be converted into our T3. And then at the peripheral tissues, they can easily convert them and use them as they are required. Things that are going to increase our thyroid stimulating hormone, things like pregnancy. You obviously need to up your metabolic rate if you're going to grow another human. So not surprising, we see an increase in our thyroid stimulating hormone coming from our anterior pituitary. And then prolonged cold. So when we look at the pathologies, we discover that one of the problems with people who don't have enough thyroid hormones is that prolonged cold will actually put them into a crisis situation because you use up all of those thyroid hormones really quickly. So being in the prolonged cold can be detrimental in a lot of cases. Things that are going to stop you from releasing thyroid stimulating hormone. So our growth hormone inhibiting hormone, also called somatostatin. So it comes along and says, okay, stop growing. So if you're not growing anymore, your metabolic rate is decreasing. And we see this sort of as we age as well. Increased levels of our glucocorticoids. So remember, these guys are our stress hormones coming from our adrenals. And so if we're having lots of stress, we're going to actually shut down our metabolic rate a little bit, which this, again, after high levels of our stress hormone out there. And we'll be able to link that in a little bit better when we look at our adrenals themselves. Estrogen and testosterone. So of course, if you're having high levels of those adrenocorticoids, or the androgens, and then really high blood levels of iodine itself. So if you're having really high levels of iodine, it's going to say, okay, well, we don't probably need to keep making more of our thyroid hormones at this time. Which brings us to our parathyroid. So we haven't really talked too much about how the parathyroid works, but the parathyroid is there to counter our calcitonin. So we talked a little bit about calcitonin before, and in class we certainly touched on it. And our calcitonin is there for when you have high levels of blood calcium. You need to go and put that in your skeleton. So when we have lots of calcium, we might as well store it in bones. So that's going to be our osteoblasts, and they're going to build some bones. Our parathyroid, on the other hand, is more concerned about low blood levels of calcium. Low blood calcium levels are going to mean that our heart is not going to beat. So we have our parathyroid gland. It's at the posterior part, or tucked in behind the thyroid itself. Now, if you need to remove your thyroid, they have to keep part of your parathyroid, and they might just tuck it in under your clavicle. And it has our chief cells. So we've seen chief cells before. They like to call them chief cells when they have an important function. And our chief cells are going to make our parathyroid hormone whenever our calcium levels get low. So we don't want to have low calcium. It's really hard to write with the touchpad. And so when those calcium levels get low, we can see here that basically those low levels of calcium mean we can go in and steal it from our bone. We can break it down. We'll get our osteoclast to come in and chomp it up. So there's my little osteoclast. And so he comes in and chomps, releases some enzymes, and therefore releases the calcium that has been stored in your bone. So that's your first step, is go and get it from the bone where it's been stored, thankfully by your calcitonin. The other thing it can do is it can say, hey, kidneys, instead of peeing out all that extra calcium, can you resorb a little bit more for me? And the third thing is to actually have your intestine, your small intestine here, reabsorb more calcium from your food. Now, obviously, if you're older or if you've had some scar tissue, reabsorbing calcium might be a limiting factor for you. All of that will release your calcium back into the blood until you have those little monitors that are saying, oh, calcium's good now, and you can shut down your parathyroid hormone from being released. And at that point, that's your end of your negative feedback loop. So our skeleton is stimulated to be broken down and release the calcium. Our kidneys are stimulated to keep more calcium, and our small intestine is stimulated to actually absorb more calcium. All of those things are jobs of the parathyroid. So that just breaks it down to the osteoclasts, resorption, and of course increased absorption. So that's pretty much it for today on that little section. If you have any questions, just let me know.